Tony Talk.
Hey Tigers, welcome back to TonyTalk.ai, the show where AI isn't just smart, it's sexy. I'm your host, Tony, and today we're diving into something you experience every single day, recommendation systems. Before we dive in, here's what we'll cover in this episode. 1. What recommendation systems are. 2. Why they're crucial in today's platforms. 3. The key algorithms behind them, from simple averaging to deep learning. 4. How companies like Netflix, Amazon, Spotify, and TikTok use them. 5. Metrics to measure success. 6. The challenges and ethics involved. 7. And what the future holds for recommendation systems. And guess what? I'm not doing it alone. Joining me is the brilliant, dazzling, and fierce, the Tigress Data Scientist herself, Marissa. So, Marissa, set the stage. What's a recommendation system?
Hey Tigers! Ready to figure out why Amazon keeps recommending cat pajamas at 2 a.m.? A recommendation system is a subclass of machine learning algorithms that predict user preferences. These models analyze large datasets of user interactions, such as purchases, to generate personalized suggestions. From a modeling perspective, rec systems can be categorized as supervised learning tasks. Predicting a rating? That's regression. Predicting whether someone will like something? That's classification.
So it's like data matchmaking?
Exactly. These systems power everything from Netflix to Spotify and TikTok. They're the engines behind personalized experiences online.
Tell us, why do recommendation systems matter?
In e-commerce and media platforms, over 30% of revenue can come from recommendations. Think of YouTube's Up Next or Amazon's You Might Also Like.
Rest in peace, Blockbuster Video.
These systems boost engagement metrics like time on site, click-through rate, and conversion. On the back end, they help companies optimize supply chains, marketing campaigns, and inventory.
If they guess wrong, I'm bailing. Fast. How simple systems work.
The most basic technique is averaging. You compute the mean rating for a user or an item.
Sounds basic.
It is, but it ignores the actual interaction between a user and a specific item. Two users may both rate highly on average, but for different reasons. It's also static. It doesn't adapt well.
Law of large numbers in action.
Exactly. Simple but shallow.
Moving beyond the simple stuff, let's explore content-based filtering.
Content-based filtering looks at the properties of items. If you liked Inception, the system might recommend Tenet because of similar genre, director, or themes. We use cosine similarity to measure how similar two items are in a vector space. A cosine of 1 means they're identical in direction. We also use TF-IDF to represent text data by emphasizing terms that are unique to specific items. For non-text content like images or audio, convolutional neural networks, CNNs, extract patterns, like textures in fashion or tempo in music, to match preferences with similar multimedia content.
Now that's deep, literally. What if you group me with my fellow TV-loving and foodie?
That's clustering. We use k-means to partition users into k-groups based on their behavior vectors. The algorithm minimizes intragroup distance and maximizes intergroup separation. For more complex data distributions, we use Gaussian mixture models, GMMs, which assume that data points are generated from a mixture of multiple Gaussian distributions. This lets us capture more nuanced patterns.
So, I'm never alone in my weirdness. What about collaborative filtering?
Collaborative filtering focuses on user-item interactions rather than item features. There are two main types. 1. User-based collaborative filtering. Find users similar to you based on past ratings and recommend what they liked. 2. Item-based collaborative filtering. Find items similar to those you liked and recommend them. Techniques include 1. K-nearest neighbors, KNN. Identify the top K similar users or items using similarity measures. Common similarity metrics including cosine, similarity including angle between rating vectors, and Pearson correlation including linear relationship between users' ratings. 2. Matrix factorization. Decompose the user-item interaction matrix into lower dimensional user and item vectors, uncovering latent preferences. Popular methods include SVD, ALS, alternating least squares, and SGD-based factorization. 3. Implicit feedback modeling. Instead of explicit ratings, models learn from signals like clicks, views, purchases, and likes. Frameworks like implicit ALS handle these types of feedback.
Real friendships have been built on less. Let's complete the puzzle. Tell me about matrix estimation.
We start with a sparse matrix where rows represent users, columns represent items, and known values are scattered ratings. Our job is to estimate the missing entries. We use singular value decomposition, SVD, to reduce the matrix to latent features, lower dimensional representations of users and items. Principal component analysis, PCA, helps us reduce dimensionality while preserving variance. Non-negative matrix factorization, NMF, adds the constraint that no negative values are allowed. Helpful when ratings or interactions can't be negative.
Elegant and nerdy, my favorite combination. Let's make the matrix better.
We use loss functions like mean squared error, MSE, for numeric prediction or hinge loss for ranking. These functions measure how far off the predictions are. Regularization helps avoid overfitting by penalizing large model parameters. This improves generalization. Training is done using stochastic gradient descent, SGD, or alternating least squares and ALS to minimize loss iteratively across millions of data points.
Down the slope of error until we find the best model. What if my tastes change?
That's where sequential models like TimeLSTM or GRU4Rec come in. These are variants of recurrent neural networks that incorporate temporal dynamics. They use sequences of past behaviors to predict future ones, capturing session trends, recency, and seasonal patterns. They're especially useful in apps like e-commerce and music streaming.
History always predicts the future.
Exactly.
Neural networks. Lay it on me, Tigress.
Models like wide and deep combine memorization, wide, and generalization, deep. The wide part captures interactions from feature crosses, while the deep part uses neural networks to learn high-level abstract patterns. It's great for sparse data like clicks or purchases. DeepFM, or Deep Factorization Machine, enhances this by learning both low-order and high-order feature interactions in a single model, using FM layers for memorization and deep layers for nonlinear learning. Transformers are deep learning models originally built for natural language processing. Unlike RNNs, they don't process data sequentially. Instead, they use self-attention mechanisms to evaluate the importance of every item in a user's history at once. In recommender systems, models like BERT4Rec treat sequences of user item interactions like a sentence, predicting masked items the same way BERT predicts missing words. This helps capture long-range dependencies in what users engage with across time and context.
You have brains made of math. Sexy. Let's talk about key metrics for evaluation.
We use precision at K, relevance in top K recommendations, recall at K, coverage of relevant items, AUC, area under the curve for classification, and NDCG, normalized discounted cumulative gain, for ranking quality. RMSE, mean squared error, measures the accuracy of rating prediction.
Precision of what we recommended. That's true love.
Recall, of what you would have loved, how much did we recommend?
Finding the balance is an art. Let's give our viewers real-world examples, Tiger.
Netflix uses matrix factorization with regularized SVD and side information like genre and time. Their top picks adapt to your viewing profile. Amazon relies on item-to-item collaborative filtering and product embeddings. They integrate purchase history, views, and even browsing dwell time. Spotify blends collaborative filtering with audio feature extraction from CNNs. It clusters users into taste profiles and uses playlist-based learning. TikTok uses a transformer-based ranking model trained on watch time, replays, shares, and content embeddings to personalize the For You page.
Everyone is using data science to bring home the cheddar and make my playlist better. Recommendation systems face several key technical and ethical challenges, including cold start problems, data sparsity, overfitting, popularity bias, and several more. What are the challenges and biases, Tigress?
Yes, including cold start problems occur when new users or new items enter the system with no prior data. Without historical interactions, it's difficult to make meaningful recommendations. Solutions include leveraging user demographics, content-based models, or hybrid approaches. Data sparsity happens when the user-item interaction matrix is mostly empty. When users interact with only a tiny subset of available items, collaborative filtering models struggle. Dimensionality reduction techniques like matrix factorization and embedding layers help combat this. Overfitting is another issue, when a model learns the noise in the training data instead of the underlying patterns. Regularization methods, dropout layers, and cross-validation are critical strategies to generalize better. Popularity bias means the system tends to recommend already popular items, ignoring niche or diverse options. This creates a cycle where a few dominant products or artists get more exposure. Feedback loops arise when recommendations shape user behavior. For instance, recommending only viral songs eventually narrows user tastes, leading to less diversity. Solutions involve exploration techniques and randomization. To combat these issues, fairness-aware models are being developed. These aim to distribute exposure more evenly and prevent systematic bias against minority groups. Active learning techniques allow systems to smartly select which new data to gather, making the learning process more efficient and reducing biases over time. Finally, ensuring ethical AI means focusing on 3 pillars. 1. Ensuring diversity in recommendations by introducing serendipity and variety. 2. Avoiding filter bubbles where users are only shown reinforcing viewpoints. 3. Protecting privacy by minimizing personal data collection and adopting methods like federated learning. Back to you, Tiger Leader.
Tigers don't have leaders, darling, but tigers must use data responsibly. Before we part and I get to the demo, what are some of the future trends?
There are 4 powerful trends reshaping the future. First, there is graph neural networks, or GNNs. These are social-aware recommendations. GNNs extend deep learning to data structured as graphs. Think users, items, and their relationships as interconnected nodes. They are important because traditional recommendation models often treat interactions as isolated events, missing the rich structure of social influence and item similarity. GNNs capture these multi-hop relationships like friends of friends, or items co-liked by similar users, allowing for more nuanced and accurate recommendations. Use cases include platforms like TikTok and LinkedIn. Use GNNs to consider not just your behavior, but also that of your connections by enabling socially aware and trust-based recommendations. Then comes federated learning for decentralized privacy. Federated learning, or FL, allows AI models to be trained across many user devices like iPhones without centralizing the raw data. FLs addresses growing concerns about data privacy and regulations like GDPR. Instead of uploading personal data to servers, only the model updates are shared. This preserves user confidentiality while still enabling personalized recommendations. A case example includes Google's Gboard, which uses FL to learn personalized next word predictions across millions of devices without ever seeing your keystrokes. Then we have Contextual Bandits for real-time personalization. These are a form of reinforcement learning. These contextual bandits dynamically learn which action to take based on real-time user context, such as time of day, device, or location, for example. Contextual bandits are important because, unlike static models, contextual bandits adapt on the fly, balancing exploration like trying new things with exploitation like using known preferences, which is critical for engaging users with evolving tastes. Examples include news apps like Yahoo News, which use contextual bandits to serve personalized headlines that adjust based on current events and your reading behavior. Finally, Explainable AI, or XAI, which are transparent recommendations that focuses on making black box recommendation models more interpretable. This explains why a particular item was suggested. This is better because it gives users and regulators increasingly demand transparency. XAI builds trust and accountability by offering insights like, "This movie was recommended because you liked X and Y." Companies like Netflix and Amazon are exploring explainable models to give users better control and understanding of their recommendations, which in turn improves satisfaction and retention. Together, these technologies push recommendation systems beyond one-size-fits-all, making them smarter, fairer, more respectful of privacy, and aligned with how real-world human behavior unfolds.
The future is private, explainable, and still spooky smart. Melissa, I want to thank you so much for joining me on TonyTalk.ai. You are one smart tigress.
Anytime, Tiger, bye.
Now let's get to the business, a demo. Today, we're cracking open a recommendation system project I tackled during my time in the MIT Data Science program. Yup, this was one of the assignments that kept me up past midnight wondering why pandas can't just clean the data for us. Let's set the scene. The context? Everyone from Amazon to Spotify wants to serve you what you'll like before you even know you like it. And that's where recommender systems come in. Our goal: build a system that predicts what books a user will enjoy based on past behavior. Essentially a book sommelier, powered by machine learning. The dataset? We used the book crossing dataset, which includes 3 files: users, books, ratings. The ratings file was particularly juicy. 1.1 million entries where users rated books from 0 to 10. But before we could feed that into any model, we had to do some prep work. First, we installed the Surprise library. And no, it's not for birthday pranks. Surprise is a specialized Python library for building recommender systems, especially collaborative filtering models. Other tools in our toolkit included Pandas for data wrangling, NumPy for numerical ops, Matplotlib and Seaborn for visualization, scikit-learn for metrics like precision and recall, and Surprise, of course, for the modeling. We loaded and explored the data, starting with a basic look at shapes, nulls, and distribution. One thing stood out immediately: the ratings were skewed, and over 70% of them were just zeros. That's like reviewing a restaurant by walking past it and eating nothing. We dropped all rows with rating 0 because they didn't represent meaningful user preferences. Next, we merged the ratings and books datasets to create a unified table, only keeping the columns that mattered: user ID, title, author, and rating. This let us associate ratings with actual book titles instead of cryptic ISBN codes that look like rejected serial numbers from NASA. We also analyzed the distribution of ratings and user behavior. Most users rated very few books, while a few power users rated hundreds. Classic long-tail distribution. And on the book side, the most popular books had thousands of ratings, while many were rated once and probably by the author's mom. With the data cleaned up, it was time to test different recommendation strategies. Model 1: Rank-Based Recommendation System. We started with the simplest model, just recommending the most popular books. This is the New York Times bestseller list approach. It doesn't care who you are. If everyone else liked it, you'll get it too. Pros: fast, scalable, zero personalization required. Cons: everyone gets the same results. So if you like sci-fi and this week's hit is Pride and Prejudice and pastrami, too bad. Great for a cold start, but useless once you want personalization. Model 2: collaborative filtering. Using KNN, user-based. Here, we compared users based on how similarly they rated books. So if you and I both love sci-fi thrillers and hate romance novels, the system will recommend to me books you've rated highly that I haven't read yet. We used Canon Basic from the Surprise library. The results? Precision at 5 and recall at 5 were modest. It struggled with users who had very few overlapping books with others. Sparsity hurts. Observation: it's great when users have similar taste and enough overlap, but fails when there's too little shared history. It's like trying to bond over movie taste with someone who's only seen Shrek. Model 3: item-based collaborative filtering. KNN with means. Instead of comparing users, we compared items. In this case, books. The logic: if Harry Potter and Percy Jackson are both loved by the same people, then if you like one, you'll probably like the other. We used KNN with mean centering to adjust for users who always rate high or low. This model performed better than user-based filtering in our case. Why? Because while users are flaky, items are stable. Books don't change behavior, people do. Item collaborative filtering gave us more reliable neighbors and slightly improved precision and recall metrics. Model 4, Matrix Factorization, SVD. No, this is not something you caught during a college party. Now we're talking power tools. SVD, singular value decomposition, breaks down the user item matrix into latent factors. In non-nerd terms, it finds hidden dimensions of preference, like enjoys dystopian fiction, but only if there are dragons. We trained it using the surprise library's built-in SVD algorithm. Why was SVD the best? It captures nuanced patterns beyond direct co-ratings, handles sparsity better than neighbor models, scales well to large datasets. It's like comparing a personal shopper who knows your taste to a mall directory suggesting whatever's trending. We measured each model using precision at K. Of the top K books recommended, how many were actually relevant? Recall at K. Of all the relevant books, how many did we recommend? Both are important. Precision keeps users happy by avoiding junk suggestions, and recall ensures we're not missing out on good ones. So what did we learn? Popularity-based models are fast, but dumb. User-based collaborative filtering is fragile. Item-based filtering is more stable. But matrix factorization, that's the real MVP. It's not just about predicting ratings. It's about understanding preferences, patterns, and context. And that's what makes recommender systems such a fascinating field. You're not just writing code, you're learning how people choose, think, and fall in love with content. There you have it, Tigers. Recommendation systems? Smash that like button, subscribe if you want your AI to be smarter than your coffee machine, and leave a comment. Which part of data science are you most excited to learn next? Until next time, stay smart, stay curious, and as always, treat others how they want to be treated. This is TonyTalk.ai signing off.